So I'll just put minus over here so that you can see like after the process happens, the error term, like the process variable gets changed over here. So what you want to do is you take that process variable and you have the entire error over here. So what you do is you subtract that so that like it's basically like saying like it has moved this much. So cut it from the original error so that you can go on with the next output part. So yeah, like we are going to be taking a transfer function. Like what I am using here is s square plus 6s plus 10 by s cube plus 7s plus 1. You can just type in the coefficients of here, coefficients over here. So I'll be typing those. So basically, this is our transfer function. Like this is what the robot does when it moves, what the robot does to the process variable when it moves. So I'll just show you how the function looks. So like this is what the function actually is. Like as you can see, like there are many oscillations for the robot to go to the uh, set point. So what you do with the PID controller is you decrease the amount of oscillations. You decrease the, as you can see here, like it's not even close to the set point that we have. Like 1 is our set point, so it's not even close to the 1 at 20 time. So what you want to do is you want to have the minimum error over here and you want to achieve that fast. And you don't want these overshoots because like imagine a robot oscillating, like if you want it to turn to the right and imagine it oscillating back and forth until it reaches the point where it has to reach at infinity time. Like it keeps on oscillating till it reaches there. So you use PID controller or any control system to achieve that point. And yeah, so I'll repeat the transfer function part. Like what a transfer function is it's basically something like think of it as a plant. Okay, there's some input going into it, and there'll be some output. What it does is like you give it a process variable, and it manipulates it, and it sends the output signal. So the output signal is something that has been delivered to the like that has been done by the robot. So you have the original error and you have this thing. So what happens is from the original, this much has been done. So you have to subtract it. That's what we are basically doing. We have an original error that's coming and there's some process that's being done. And after that, you just subtract it. And this keeps on going and like this runs as a loop until the error is basically 0. And like you can see here, what happens is you give it the error is 1. Okay, so the transfer function is trying to reach there and it's slowly going to it's just oscillating, and like you can see like it's not reaching the value there. So you use the controller to get to that point. Like you can see, like if I change this to 2, I'm changing the proportional value here. You can see like there's a lot of change that has happened here. The oscillations are reduced and you can clearly see the difference at the set time, like set point and the value that we are achieving. Like this is the steady state error that we are getting. And we want to minimize this because if there's a steady state error that's accumulating again and again, it'll be a problem. So uh, for that, we'll just be increasing the p-value. Okay, so you want the explanation of each block. So step function is like you can see here. You can see that step time. Uh, like this is the final value, this is the initial value, and this is how much time it takes to change. So basically, what happens is like you can see here, this is the step function's value. Like this yellow line is the step function's value. So basically, this is the step, and from time less than 0, there's no value here, it's just 0. And after that, from t equals to 0, it becomes 1, and it just keeps the constant 1. So we are trying to achieve that 1 with our transfer function over here. So this, what this block does is, it's pretty simple. Like you have this error, and it will be going in with a plus sign, and you have this process variable that is over here, and it will just go and subtract into the error term, and it will just be transferred again. So let's just say like you have the initial error as 1, and it goes through this process, and you have some process variable over here. So what it does is it takes 1 and it subtracts the process variable from it, and it goes back. It's yeah, it's pretty straightforward. And we have the PID controller blocks. So you have the proportional, integral, and derivative things. Okay. 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 So here is the formula for that. Like you can see, like this is what the Laplace transforms are, like 1 by s for the integral, as we have seen in the previous slides, and this is for the derivative. And these are the respective gains. So you can see like direct multiple for proportional and integral times I, and we have the derivative times derivative gain. So this is the PID controller block, and you can set like saturation. Saturation is something like it limits the value from going. Like take a at t equals to 0 seconds, the step function directly grows from 0 to 1. At that point, like if you take du by dt, it's just infinity. So what it does is like it cuts the upper limit, it sets the upper limit and lower limit. We don't really require it right now. What it does is it's basically like sets the upper limit and lower limit. Like we can set it as 2 because our uh, function goes from 0 to 1. We can set it as 2 because we have oscillations and all. So that's uh, like you have these multiple features. Like you can directly tune here, or you can try the trial and error method over here, filter coefficient to smoothen the graph or something. And you have like changing the types over here. Like you can change the type you want the formula to be. Like you can have the proportional gain outside, and proportional gain into the integral gain gives us the integral gain. So it's like you can change the type of function that you want to have over here. Like you can make this using gain blocks and like proper transfer functions, but this is preferred because you have so many more options here. Yeah, so mux block, as I said, like it shows the graphs of two functions of the same data set in the scope or in any output device. Yeah, yeah. So again, I'll start from 1. Yeah, here this is what the transfer function actually is. Like this is the graph of transfer function without any uh, controller that's set up for it. You can see like this is the transfer function. It's a quadratic by cubic, and that gives you a graph of similar kind like this. And what you want to do is you want to minimize the setting time. You want to minimize the steady state error. You want to minimize the overshoot, and you have to reduce the oscillations. So to do all this, you use a PID controller or any controller, and you do optimization for this. So if I change the, when I put the proportional one, it's basically the transfer function, and I can change the values over here. As you can see, the oscillations are reduced, and you can somewhat see like there's a setting time for it. Like after this, there's no like you see that there's no changes here. It's pretty much constant value. We call this as setting time. Like setting time is generally between 5% of the 5% of the desired value, 5 or 2%. If you want more accuracy, you go for 2%. You have to reduce the setting time. Like for this change, it's taking around what, like 18 seconds. You want to reduce this. You want to achieve it like say 2 seconds. You have to change the values of PID accordingly. So let me increase it. Now you can pretty much see like a steady state error is reduced, and the oscillations have decreased even more, and the overshoot also decreased. So as Kunal mentioned earlier, you have these criterias like rise time, percent overshoot, and you basically try to find the optimal values for what you want to achieve. Let's say you want to achieve the minimum rise time, and you don't really care about the steady state error. Like it has to be in some value, but you are more focused on rise time. You put the values according to what you want and check the performance of the controller. Yeah, so if I keep 5, you can see that like oscillations are almost down to 2, and the steady state error is reduced even more. So we can increase it. Let's go to 10. Here you can see like this, the steady state error is almost none, and the settling time is also pretty good. Like you can see like at almost like 5 seconds, it's ready. Like it's settling, and the overshoot is also pretty low, and the rise time is also pretty good. So yeah, we'll be using proportional 10. Like we can increase this value, like let's say 100. It gives us even better graphs. Like you can see like these two graphs are almost meeting at this point. Like there's almost no steady state error. But if you if you zoom in, like you can find some minute steady state error, but pretty much it's like the same. Mm, for demonstration purposes, I'll just put it 10 because the graph is like the overshoot is too low to show anything. You can see like, yeah. Now let's increase derivative in, yeah. Yeah, you can see like overshoot is reduced. The overshoot is reduced, but you can see a tiny bit of steady state error here. So to reduce the steady state error, we use integral. Yeah. Now the steady state error is reduced, but the time taken to set is increased. So basically what we use is like proportional is something uh, to reduce the oscillations and to get to the point of settling, and to get to the point of settling faster, because like proportional, it's directly multiple of that. So you get this instant high changes of value. So you get to the point of settling faster, but it has its own issues. Like if you increase the proportional too much to the point like where like let's say we increase it to 10,000 or even more. So what happens is you see the overshoot over here, right? What happens is this overshoot becomes too large. Like as Kunal said earlier, if the function that we are sending is bounded, we want the output to be bounded. But what happens is at some point it increases so much that it becomes like it tends to infinity. So at that point, it will become so unstable that we won't be able to control the robot anymore. Yeah, so you want to increase the proportional gain till the point where you're getting as low overshoot and faster settling time. And after that, you have to stop increasing, or if you keep on increasing, the overshoot gets too much and it becomes unstable. And as you have seen, like derivative is something that reduces the overshoot because it measures the rate of change of process variable. And so what it does is like, if the overshoot, like if it's increasing too much, it can see like if the slope is too much and it's going up, what it does is it basically controls it and it reduces the overshoots accordingly. And integral is like it sums up the all previous errors. So uh, while you're going to the settling point, you'll just basically reducing the steady state error. So after summing all the previous things while getting to the settling point, it reduces the steady state error. So yeah, you can increase. The overshoot increased a bit, but you can say like there's no error over here. Like even if you zoom in, like you can zoom in with this. You can see like there's almost no error. You have some oscillations over here, but generally what we consider as settling time, as you have seen, is 2%. Now 2% of one is like 0.02. So 0.98 is too far. It's like 0.002% or something. So yeah, there's not much any settling time, and also the steady state error is very low. So this is how you do the tuning of PID controller. Basically, this is the trial and error method. You basically have some different methods too, like Nicholas method. And in trial and error method, you just keep on changing these values so that you will get the best graph here as possible. So here we can also calculate the rise time and percent overshoot and all. You can see like so it's around like 1.05 at the 1 point, like, oh sorry, it's not 1.05. I've set the step to start at the time t equals to 1 second. It generally starts at 0 seconds, but yeah, we'll take over here like 1.05 seconds, and to reach 90% of one, that's 0.9 over here. And you can see like it's around like 1.3. So the rise time is around 0.25 seconds. So if you want to minimize this value, you increase KP, or yeah, you increase KP. So uh, based on what the requirements are for your robot, uh, there are like different types of other methods too. Like uh, you give different values that you require weights, and you expect them, like if you want the energy consumption to be minimum, you give them higher weights, or if you want this to turn fast, you give them weights. And yeah, so basically you can uh, based on the desirable performance that you want, you change the controller values, and you have an auto tuning option over here, which gives like the optimal of everything. Like it considers all the parameters and it gives the optimum of what you want. Yeah, that's pretty much about the PID controllers. Yeah, if someone has any doubt.
I guess there are more. So you can continue.
Yeah, Kunal, like uh, if there are any doubts in the chat box, you can just ask me.
Yeah, I am reading. Please send any doubts that you have in the chat. Can you take a look at the chat box? There seem to be a couple of them.
First, I'll show you the, yeah. Kunal, can you like share the screenshot of this?
We'll be sharing PPT later, so you can take a look at it later.
Wait, I don't understand this. What's your doubt actually? How to graph the idea to visualize minimizing time taken to correction while not compensating speed. See, like to minimize the correction time, you increase the speed of rotation, right?
Kunal, allow participants to unmute themselves.
Yeah, this.
See, like you can increase the value of integral until the point where it, see, like if you increase the integral too much, it's going to affect the overshoot. So you can increase it until the point where it settles the, like the steady state error is minimized. And like as anything, you should not increase it too much. Then it will cause like overshoot problems.
So guys, if you have any doubts, you can unmute and speak.
Yeah, so here, like as Kunal said, like differential equations are hard to solve. So we'll be using Laplace transform and convert it into frequency domain, which is easier to solve.
I guess there were quite a few doubts regarding Laplace when I was taking. So I could go over it again. So yeah, the Laplace transform, basically the function that we are getting, like I, let's say the distance covered that is being covered by a robot. We are getting it as a function of time, and that happens to be a differential equation. So now differential equations are usually very difficult to solve. So we use this technique that is called the Laplace transform. So using the formula shown, we transform the function x of t, that is the function in time, to the function capital X of s, which is a function in s, which is the Laplace variable.
Yeah.
Uh,
So see, like there are some differential equations like that use two variables, like y of t and x of t. So using like these, there are some standard Laplace transforms. So using these, like you can basically solve them. Yeah.
it is very important. Just a second. So yeah, here in this slide there are a few common Laplace transform pairs. So basically, these are very helpful to solve equations that we might come across while designing a PID for our robot. So we will be sharing these slides later, so you can have a look at it later, and these will help you with your assignments. And yes, once again going over the transfer function. So how we are obtaining it, right? So here we are taking a RC circuit and our input voltage that has been applied E input, right? Uh, that is a function of current, which in turn is a function of time. So basically, our input is a function of time, right? Let's say the current in the circuit is varying as I of t, and applying basic like Kirchhoff's laws, we can figure out that E input is Ri plus Q by C, where Q is basically the charge in the capacitor, which is written as integral of current over time, IDT, right? And then we have the output, which is the E out, which is the voltage across the capacitor, which is given by 1 by C times integral over IDT, right? And these, as you can see, are differential equations. And in order to solve them, we take the Laplace transform of these functions. So capital E input is the Laplace transform of small e input. Okay. Now taking the Laplace transform, we get E in is R into I plus I by CS. Here, from the previous formulas that were shown, uh, the integral term, when put in a Laplace transform, we get I by S. Integral I dt gives you I by S. So that's how we have obtained the Laplace transform for the input and the output. And the transfer function is the ratio of the Laplace transform of the output by the input. So here in the slide is a bit reversed, but that's fine. So G of S is basically how we show the transfer function. In this case, would be 1 by 1 plus RCS, where the I of S terms have been cancelled. So this is how we have obtained the transfer function for a simple RC circuit. And using these methods, you can get the transfer function for your process variable, whatever you are trying to do using your PID.
Yeah. So like if you were thinking like what's the use of this? So after calculating this using like standard Laplace transforms, you can convert this back into time domain also. So if you want like to say you wanted to solve some differential equation in time domain, you use Laplace transform and you finish it. After that, you can transfer it back into time domain. Like suppose like 1 by 1 plus s is some like e power minus t u of t. So you can like transfer it back into time domain.
Yeah. So you use the inverse Laplace transform technique there.
Okay. Okay. This is too.
So if you have anyone else, please feel free to unmute and ask. guys, if you want us to go over any of the parts of the presentation.
Yeah, if no one has any doubt, we'll be ending the meet. Yeah, guys, you can leave.
Just I'll take the attendance just a minute.
Oh, okay, okay.